Welcome. Let's take a look at introducing the notion of an antiderivative. Before we talk about antiderivatives, let's think a few minutes about inverses and how we've seen them in algebra. Here I have three different equations, and in the process of solving each of these equations, we use inverse operations or inverse relationships. For example, in our first equation, we see 3x minus 4. We will use the inverse of subtraction or addition to help us isolate the variable x. So we would add 4 to both sides of this equation. We would end up with 3x equals positive 4. We still haven't solved for x, so we would use the inverse operation for multiplication or division to finish our process of solving for x. So we'd have x equals 4/3. So in solving this equation, we use the inverse operations for subtraction specifically and for multiplication. Now, there are other types of inverses. For example, we have here x squared equals square root of, or equals 5. If we wish to solve this equation, we would use the inverse idea for x squared. In other words, we would take the square root of both sides of this equation to end up with x equals plus or minus square root of 5. So the squaring function and the square root function are inverses. Over here on the right, we have the natural log of x minus 4 equals 0. And to solve this equation, we could use inverse functions. The inverse of the natural log function is the exponential function base e. So we could take and exponentiate both sides of this equation. And since the exponential function base e and the natural log function are inverse functions, we end up with x minus 4 equals, and then e to the 0 is 1. And at this point, we could use the inverse of subtraction, which is addition. So add 4 to both sides, and we get x equals 5. Now, the reason I went through this is I want us to take a view of antidifferentiation as being similar to inverse functions. So let's take a high-level perspective on this. If I have f of x, which is equal to x to the n, so a polynomial-like function, and I find its derivative, well, the power rule tells me that the derivative of x to the n is n times x to the n minus 1. So using this rule, then I could apply it, and I'd get f of x equals x squared, which would mean that my derivative would be 2 times x to the 2 minus 1. Or more simply, I could just say this is 2x. Now, what if I start out knowing that my derivative is 2x? And I want to go backwards. I want to undifferentiate. I want to find the original function. Well, because we just took the derivative up here, we know that the original function for the derivative being 2x could be x squared. But notice I have the question marks there. Could it only be x squared? For example, could my original function have been f of x equals x squared minus 1? Or f of x equals x squared plus pi? Or even f of x equals x squared minus 2/3? For each one of those functions, my derivative would be 2x. So notice in that differentiation process, if I were, for each one of these, if I were to find the derivative, I would lose the information about any constants. So when I take the derivative of x squared minus 1, the derivative of the minus 1 is 0, and it doesn't appear in my derivative. Same for the second function. The derivative of the plus pi would be 0 because pi is a constant, so it doesn't appear in my derivative. And same here with the third one. So it's x squared, but it's a little bit more. More precisely, our antiderivative, our f of x, could be x squared plus any constant. And if all we have is the derivative to work with, then I cannot determine the specific constant that may have originated in the function. So we use this f of x squared, or I'm sorry, f of x equals x squared plus c to capture all possible antiderivatives. So a little bit about what an antiderivative is. An antiderivative of a function f of x is any function, we'll call it capital F of x, such that when I take the derivative of capital F of x, I end up with the function that I was asked to find the antiderivative of. We'll see this in a moment. An antiderivative is a family of functions which we write as capital F of x plus c, where c represents any possible constant. An antiderivative of a function f of x is written with this symbol. This is called the integral symbol of f of x dx. The dx at the end of the integral is the differential and must be included as it indicates the variable of interest. In other words, the variable we are integrating with respect to. And then this function f of x, that's referred to as the integrand. So we have an integral symbol, we have an integrand, and we have a differential. And then we refer to the process of finding the antiderivative of a function as antidifferentiation or integration, or we might say find the indefinite integral of. So those are all pieces of language that we refer to in the process of finding an antiderivative. So let's look at three really quick examples here. We have the antiderivative of 3.5 dy. So in our definition, the function that we're antidifferentiating is a constant function, and we want to find that family of functions for which this is the derivative. Now, in finding the antiderivative, we rely heavily on our knowledge of the derivative. So the antiderivative is linear, and what that means is that I can take and rewrite this antiderivative as 3.5 times the integral of 1 dy. And then down here, we know that the derivative of x is equal to 1. So when that derivative is equal to 1, that means the antiderivative is going to be x plus a constant. Well, in this case, my variable is y, my differential is y, so I will not be using x. But the antiderivative of 1 dy would be y plus c. So we'd end up with 3.5 times y plus c. Now, if I use the distributive property, I'll have 3.5 times y plus, and now this is this could be any constant, and then we're multiplying by 3.5. So if you take a constant and you multiply it by a constant, you're really just ending up with another constant. So let me write this first this way, 3.5 times c, but that's just really some other constant that we'll relabel c, because we don't know any restrictions on what this value of c is. It can be any constant. So 3.5y plus c, can capture all of the same functions that this 3.5y plus 3.5c would capture. So in this case, our antiderivative is 3.5y plus c. And all we have to do to check our work is ask ourselves, if I take the derivative of this expression, this function, what would I get? Well, I would get, if I took the derivative with respect to y, I would get 3.5 times 1, or 3.5, plus 0. And 3.5 plus 0 is, in fact, this 3.5 function that I initially started with. In our next example, we have the antiderivative of e to the p dp. So in this case, our function is going to be a function of the variable p. And we use what we know about the derivative of an exponential function. We know that the derivative of e to the x is e to the x. So if I'm to invert that process and I want to integrate e to the x, what's the original function I would have started with? Well, I would have started with e to the x plus some constant. So if I take the derivative here of e to the x plus c, what would I end up with? I would end up with e to the x, or my integrand. So in this case, the antiderivative of e to the p is simply e to the p power plus a constant. And then I can double check my work by taking the derivative of e to the p plus c, again with respect to the variable p. We would end up with e to the p in our first term plus 0, which would give us this integrand that we started with. So that would be our antiderivative. And in our last example here, notice that we have this constant multiple in front of our e to the x. So we can bring that 3 in front of the integrand, the integral symbol, and we'd have 3 times e to the x dx. And just like we did before, the antiderivative of e to the x, or e to the x is the derivative of what? Well, this e to the x is the derivative of e to the x, potentially plus some constant. So using the distributive property, we get 3e to the x plus 3c, but we're not really interested in this specific constant. We just want to be sure to capture that we have something that looks like 3e to the x plus a constant. So our antiderivative here would be 3e to the x plus c. I hope you find this helpful.